Alright, welcome back everybody. This is video 2 for section 15 of Unit 1 of AP Calculus, connecting limits at infinity and horizontal asymptotes. In this video we're going to look at some applications of limits approaching infinity, a couple of different applications, and we start with probably one of the more important ones, that of a horizontal asymptote. And here we have a strict mathematical calculus-based definition of what a horizontal asymptote is. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. The way this is defined does have, some meaningful implications for us, namely any graph will have 0, 1, or 2 horizontal asymptotes. So, graphs of functions, the number of vertical asymptotes that a graph could have is technically unlimited. Imagine, the tangent function, for instance, where we've got a periodic asymptote that happens over and over and over and over again. But with horizontal asymptotes, we're limited because this limit right here can contribute 1, this limit right here can contribute 1, and that's the only way we can have asymptotes. So either both of those statements are true, or one of them is true, or neither of them are true. It's possible that neither one of those limits will approach a finite value. All right. So once we know that, finding horizontal asymptotes is easy enough. All I need to do is find the limit as x goes to infinity of this particular function. And how you choose to find that limit is up to you. We could do it algebraically, like we learned in the last video, or we could do it numerically on our calculator, like we learned in the last video. Or after you've done a bunch of these, you realize that you can pretty much just wave your hands to find the limits, so that if you're in a situation where you don't need to show any work, you can just go straight to the final answer. But I'm going to go ahead and do this algebraically. I'm going to divide through everything by x cubed. And if I do that, we see that all of these green highlighted terms approach 0, and so this value is going to be equal to 2 over 8, or 1/4. Just like I have a pet peeve where it irritates me if people don't write vertical asymptotes as equations, same pet peeve exists for horizontal asymptotes. This is the numerical value where the horizontal asymptote occurs, but the actual asymptote itself must be an equation, namely the equation y equals that numerical value. And so that is our horizontal asymptote. So this graph has 1. And I can show you that it has 1 if we, again, take the limit as x goes to negative infinity of this function. That limit is also 1/4. Let me do that one on my calculator just to, show you refresh the different methods of finding the limits finding the limits approaching infinity. So I'll type that function in, 2x cubed plus 5x squared minus 7 over 8x cubed plus 3x, and go to my table. Hey, and I already have values approaching negative infinity, and you see that those values, as x gets bigger and bigger, are getting closer and closer to 0.25. And so it's got the same limit, and hence this one only has 1 asymptote. So that's kind of the process we go through. We examine the limit as x goes to infinity and as x goes to negative infinity. I can do both of those on my calculator if I want. I can, try and do both of them algebraically if I want, whatever the case may be. All right. Uh, Relative growth rates of functions. Another application where we can use the limit as x goes to infinity. If we have two functions, and we take the limit of the ratio of those two functions, the limit as x goes to infinity of f of x over g of x, there are three situations that can occur. Situation number one, when that limit is infinite, that tells you that the function in the numerator grows faster because the fraction is growing to an infinite value, so whatever's in the numerator has to be bigger than what's in the denominator. Then we have the situation where the limit is 0. That tells us that the function in the denominator grows faster because f divided by g gets closer and closer to 0, which means g has to be bigger than f. And then we have the third scenario, which is when they grow at the same rate if we end up with the same finite value. So let's compare the growth rates of these two functions, e to the x and x to the fourth plus 2x cubed. I don't have a way to really handle this algebraically, so I'm going to use my graphing calculator to help me decide what's going on here. So I'm just going to go ahead and take the limit of the ratio of these two functions, and then one of three things will happen. That limit will approach infinity, in which case I know e to the x grows faster. That limit will approach 0, in which case I know that x to the fourth plus 2x cubed grows faster, or that limit will approach some finite value, in which case they grow at the same rate. So let's take a look at what happens here with these two functions. So I'm going to go ahead and put in e to the x over x to the fourth plus 2x cubed. And I will go ahead and go to my table. And I'm going to put 10 in there and 100. Whoa, that got really big really fast. 2 times 10 to the 35th. I bet it won't, my calculator probably won't even be able to handle 1,000. Oh no. 2 times 10 to the 422nd. Regardless, this is growing to a bigger and bigger value, and in fact my calculator even at one point tells you, hey, this is approaching infinity. So this limit approaches infinity, therefore e to the x grows faster, since that's the function in the numerator, and we ended up with an infinite limit when we took the limit of the ratio of those two things. Okay? Next type of application, what are known as end behavior models. And we'll talk about the end behavior of functions. End behavior ties back to the idea of horizontal asymptotes. We're talking about what's happening as x goes to infinity, what's happening as x goes to negative infinity. Okay, so we're figuring out the end behavior when they approach finite values. You see this sentence right here. When these limits approach finite values, we've already seen that we have a horizontal asymptote. When those limits approach an infinite value, it shows you what the end behavior of the function is. You know, as x goes to infinity, if f of x goes to infinity, that means the function is going to continue increasing as x gets bigger. If it goes to negative infinity, the function is going to continue to decrease as x gets bigger. And so this is my right end behavior. It shows that the graph either rises forever as we move to the right, or it falls forever as we move to the right. If we do the limit as x goes to negative infinity, then that tells us our left behavior. But basically, end behavior tells us what happens with the function at its ends. It says here, an end behavior model is a way to mimic the behavior of a complicated function with a considerably simpler function as the values of x get large. So when we talk about end behavior, we're talking about what does the function act like as x goes to infinity or as x goes to negative infinity. When we talk about an end behavior model, we're actually talking about some equation that we can, replace the actual function with that behaves in the same way as x goes to infinity. Okay? So we're going to explore this. We're going to go ahead and type two functions into our calculator. We're going to type the function y equals quantity 2x cubed plus 7x squared plus 5 over x squared minus 5x plus 8. And I'm also going to type in y equals 2x. And I'm going to go ahead and make my y equals 2x a thick line so that I can tell the difference between the two when I graph them. Okay, if you don't know how to do that on your own, it's something you want to learn. My window is already the standard window. I'm going to go ahead and graph these things. And here's the initial function. And there's y equals 2x. And those two functions don't really look a whole lot like each other in this situation. But what we can do is if we zoom further and further out, these graphs are going to start to look more and more like the same function. Okay, so there I've zoomed out once. Not too noticeable yet. Let's zoom out again. But what happens here is if I zoom out a handful of times, they're already starting to look pretty close to one another. Let's do it one more time. Hopefully that'll do the trick. Where in essence, these two curves really just look like they are the exact same curve as we get further and further out. Okay, that's because y equals 2x is an n behavior model for y equals 2x cubed plus 7x squared plus 5 all over x squared minus 5x plus 8. So, how do we find an n behavior model? Well, in reality, as x goes to infinity, if you think about how we found limits approaching infinity algebraically, it gives you kind of a clue as far as how you're going to find an n behavior model. When we were finding those limits as x goes to infinity, we divided by the biggest power that appeared in the fraction, and everything that became, something with an x in the denominator approached 0. And that teaches you a very important aspect of limits as x goes to infinity, namely, when you take the limit as x goes to infinity, only the biggest power of x in the numerator and the biggest power of x in the denominator carry any power. 6x to the fifth grows so much faster than 2x as x approaches infinity that it completely dominates its behavior. And so, the biggest power of x in both the numerator and denominator dominate the behavior of this function. And so to find the n behavior model, I'm going to ignore all the other powers of x and just take those two powers of x and then simplify the result. And you would find that y equals 2x cubed is a great power function and behavior model for this rational function. All right, that's it. We've got some practice problems and more practice problems for you on what we've done in the last two videos. And for those of you who are in my class, there's a MyAP assignment for you as well. All right, that's it for this video, and that's all for section 15. Come on back next time for section 16, the final section of Unit 1. All right, have a great day, everybody, and I'll see you next time.